It's a big honor to speak here, and yeah, I'm very glad to be here. And yeah, so my topic is the cohomology of algebraic varieties. So that's a very general title, and so I can say anything now. So I guess my object of interest as some kind of number theorist I can try to, yes. So I have x. Let's put myself into like the simplest possible situation. So let's assume it's projective and smooth, the kind of thing I want to consider. And let's say it lives over, it's defined by polynomial equations with actually integral coefficients. And now the expert might intervene and say that there are actually not so many examples of this happening. So like you're allowed to assume it just lives over spec z where you localize at some prime. Then there are many examples, but I don't want to say, like you should always stick away from the primes dividing n in that case, and I don't want to keep track of this. All right, so what is such an object in first approximation? So in first approximation, you can try to understand this by looking at the complex solution to some set of polynomial equations. So that gives you some closed subspace in some complex projective space, which is some compact complex manifold. But it's somehow one which is defined by polynomial equations. With integral coefficients. Okay? Why is everybody laughing? And so I guess the goal is to understand the cohomology. I'll try not to move too much. So understand the cohomology of x. And I put the in quotation marks here because actually there's a simple reason why there's actually a lot of cohomologies of x. One reason is that one can vary the for coefficients. So one can take cohomology with coefficients. Well, the best thing, I guess, is if you can take cohomology with integral coefficients. That's pretty good. But sometimes, as will happen somewhere in the situations we will interest in algebraic geometry, sometimes you can only take coefficients in FL or maybe ZL, which is, no, here we already have these L-egg numbers. It's the inverse limit. So L is some prime. And you can either look at Z mod L coefficients or compatible systems with Z mod L to the n coefficients, or maybe you can look at complex coefficients. And on the other hand, so we have this x. It's defined by integral coefficients, and so in algebraic geometry, we actually like to regard this as a family of something like compact complex manifolds. So it has various fibers. Which I will denote by x over the finite field with p elements, which somehow live over then it's called the spectrum of fp. And so here p is also a prime. And the two primes p and l will play very different roles because one is somehow there to keep track of the which cohomology coefficients we take, and the other is keeping track of where we are. So somewhere there is a spectrum of the integers, which has as a closed point, it has all the prime numbers. And then maybe somewhere there's also some kind of infinite point. And over the infinite point, we should imagine that there we are looking at this complex manifold x of c. We have some kind of torus over there maybe. And then we also have some kind of spaces which maybe we should also imagine that as being some kind of tori in this case. But maybe of a slightly different sort, and which are maybe also some in some way connected over the space. And so the picture I'd like to fill in during this talk as much as I can is the following. So there's a picture which has two spec z directions. One is parameterizing the prime P, where somehow taking cohomology of different fibers of the space X. So we have 2, 3, 5, 7, and so on. Somewhere here we have infinity. And on the other hand, there's another spec z direction, where there's some of the prime L, which is here. So again, we have to all the prime numbers here. And maybe also we have somewhere infinity, which corresponds to complex coefficients. And so the idea in this diagram is that at some point parameterized by P and L, we have the cohomology, whatever it is, of some of the fiber at P with mod L coefficients, whatever that is. All right. And so let's get started in filling this diagram. So the simplest cohomology theory that you can think about, and I guess historically also the first one, is singular cohomology. And so here, what we're doing is, somehow we have this topological space X of C, this complex manifold, and we can just look at the singular cohomology groups of this topological space, say, and we can do this with integral coefficients, there's no problem whatsoever, so singular cohomology groups. And this really just depends on the topological space X of C. So these are very nice objects, so they are finitely generated abelian groups. They have a Poincare radiality, etc. So very nice guys. And so in our picture here, where would this go? So we're taking the fiber of X over infinity here, and then we have integral coefficients, so we have something that lives over all of here. So that's, let's see, singular cohomology. Maybe, I hope the picture, if it's not clear now what it means, it will become clear during the talk. So, so let's just go through the simplest kind of example of such an X. So we could look at the case where X is just a projective line. And so then we are looking at the singular cohomology groups of the complex projective line, which is just topological two-sphere. And so that's C in degree 0 and 2 and 0 otherwise. But let me actually better, so the interesting cohomology group, of course, is the second one. So 0's one just counts connected components, and that's maybe not so interesting. And so let's try to understand better the second cohomology group. And for this, it's convenient to look at a Meyer-Vietoris sequence. For the covering of P1 by the two semispheres, or algebraically, you can cover P1 by two copies of A1. But one is the natural embedding and one is from the other side. So in one copy you have maybe 0 in it, and on the other copy you have infinity. And so their intersection is in algebraic geometry usually denoted by GM. This stands for the multiplicative group. And so, of course, GM of C is just C star. So GM is just A1. Removes the origin. All right. And of course, if you take the affine line, that's contractible. And so if you look at the Meyer-Vietoris sequence, this tells you that there's an isomorphism between the first singular cohomology of C star and this guy we're interested in. All right. And the first thing, like cohomology of C star, some related to the fact that there's a circle, a topological circle inside C star. Or said differently, if there's a non-trivial fundamental group, then equivalently there's some kind of non-trivial universal covering space. And so this isomorphism to Z here, this is related to the universal covering which is the exponential map, which goes from complex numbers to C star. And an important observation here is that this is not algebraic, right? The exponential map is not algebraic. What one can approximate, like the universal covering is not algebraic, but any finite subcovering will be algebraic. So, and so what are the finite coverings of C star? They are just given by covering the multiplicative group by someone not totally winding up this topological circle inside it, but only winding it up like n times. So the corresponding map will be somewhere x next to x to the n. But now x maps to x to the n is a perfectly algebraic map. So so this already tells us that maybe we can't expect somehow to see all of the integers here in some algebraic way, but maybe some z mod n for any n could be seen in an algebraic way, and that's actually what happens. So that's also a general principle that all finite coverings of algebraic varieties are still algebraic. And so this brings us to the second cohomology, which is Grothendieck's famous étale cohomology. And so here, the motivating question for Grothendieck was that, well, if I have some variety which does not live all over the spectrum of the integers, but which really just lives in the fiber over 1 prime p, so if I have y just over the spectrum of fp, which you might in some of the context of this talk think of as a fiber of x over fp, but let's concentrate on something that really just lives over fp for the moment. So can one define an analog of, well, he would like to write the singular cohomology of y of c, but as so y lives only over this fiber, there are no complex valued points, so that you can't look at this. Now the reason Grothendieck was interested in this is because when Weyl formulated his famous Weyl conjectures on the numbers of solutions to polynomial equations over finite fields, he already observed that one approach to proving such a thing would be in terms of such a conjectural cohomology theory. And sometimes Grothendieck answered this. I mean, yes, Grothendieck answered this. But you can't get integral coefficients. You can only get the L coefficients, where for now L is not equal to P. And so let me explain why you can hope for this in just this very simple example of P1 or equivalently GM. So some of the H1 of GM with the L coefficients, that's just the inverse limit of the H1 GM with the mod L to the n coefficients. So this is related to the system of covers let me write the multiplicative group now, which send x to the L to the n. And we want this is really some kind of covering of the space. And so there should really be some kind of deck transformations, some non-trivial deck transformations in the situation. And so the deck transformations would be given by sending x to an L to the nth root of unity times x. Because if you raise that to the L to the nth power again, you get the same result. So where theta L to the n is an L to the nth root of unity. But it's a well-known phenomenon that L to the nth roots of unity non-trivial. Root of unity exists only when L is not equal to P. So the issue is that in characteristic P, if x to the P is 1, then in characteristic P, that means that x minus 1 to the P is equal to 0. And so, at least if you have a reduced space, that means that x minus 1 is equal to 0, so x is 1. And so that's the reason that this étale cohomology works in characteristic P only if L is not equal to P. All right. So in the situation that we're interested in, we're trying to fill in this diagram more. The thing to look at is a étale cohomology group of x base change actually to an algebraic closure of Q. So Q bar inside of the complex numbers is a set of algebraic numbers, a field of algebraic numbers. The numbers satisfying a polynomial equation with question of coefficients. And so an interesting object for us to look at would be the étale cohomology with the L coefficients. Now in characteristic 0, we're allowed to take any L. And you might think that this is not interesting because actually that's canonically isomorphic, because I defined my Q bar inside C, to just singular cohomology with the L coefficients. So you would think that there's nothing new, but actually, some of the absolute Galois group of Q is a group which commutes this field of algebraic numbers in a way which preserves all algebraic relations. And so this will automatically acquire an action of the absolute Galois group of Q now, which somehow in this example of the multiplicative group would be the action on the roots of unity. And so, and this is also isomorphic to the étale cohomology of x over fp bar with the L coefficients, as long as L is not equal to P. So in terms of the diagram now, for any P, I may have should have said this, that you should think of the, sorry. You should think of, like, I guess in this case, that's spec Z7, as a formal neighborhood of the prime 7 inside of the spectrum of the integers. So it's like power series in the variable 7 that you have there. And so this means that geometrically, it's a completion at any prime P, we have somehow filled something in which lives everywhere, works for all the primes, except at 2. So we have to leave out 2 here. Then there's also something at 3, which, so I have to leave out 3 here, and so on. So this stuff is H1 at all. Let's see 7 coefficients here. All right, but somehow it doesn't live, so it only lives near the completion that's any prime, but not everywhere. All right. Good. Okay, so if you fit in much more already. But something that worked Grothendieck is that there's nothing, somehow if I'm interested in something characteristic P, then there's no periodic cohomology theory. And I want to get there, but I will get there through some one intermediate cohomology theory. Known as the Ramco Module. So I guess the intuitive idea behind the Ramco Module is that if you have holes in your space, which you, for the moment, you should maybe think of as some complex manifold. I'm sorry for this. So these are measured by singular cohomology. Then they're in some sense equal to the obstructions to integrating differential forms. Globally. The prototypical example, of course, being on C star, so C minus 0, we have the differential form dx over x. And we would like to integrate this to log x, but there's a 2 pi z ambiguity. Well, of course, 2 pi I is the integral over S1 of this differential form dx over x. So because as you integrate once around the circle, this differential form, you get something non-zero. You can't find a global primitive of the differential form. And the nice thing about this example, what you see in this example, is that this differential form, which gives you the obstruction, is algebraic. And it's the theorem of Grothendieck that in general, the obstructions can already be seen on algebraic differential forms. So in our situation, what we can do is, starting with our x, or a guy over spec z, we can build an algebraic de Rham complex. So you have the sheaf of regular functions on x. And you can differentiate them. You get a one form on x. So I should maybe say algebraic one forms. And so on. Wait, should I take another pen at some point? And then it goes on until D, which is some of the algebraic dimension of x. And then so the Ramco module of x is defined as, okay, now I have a complex of sheaves, and so the way to take cohomology of that is to take what's called hyperchomology, but anyway. So I have this complex here, omega x bullet, the hyperchomology of this. And so because we're working with something over the integers, so those are still finitely generated Abelian groups, they satisfy Poincare radiality, etc., which, by the way, was also true, I mean, with the L modules here for the entire cohomology. Very nice, guys. But there is something new. They are not the singular cohomology groups of the compact complex manifold, but But there is a comparison theorem which says that, so if you take your Ramco Module groups and tend them up to the complex numbers, then first of all, you can also realize them as the Ramco Module groups of this compact complex manifold. But on the compact complex manifold, you have some, so this is essentially what's called the Poincaré lemma, or a consequence of that. That this is just computing the singular cohomology groups again after you extend scalars to the complex numbers. And so you might, so what you get here is some finite dimensional C vector space with two Z lattices inside, but actually they are very different, and that gives rise to the famous periods in algebraic geometry. So we said H1 Ram and H1 singular are very different Z lattices. So in the simplest examples, they differ by exactly what we computed above. So where we compute dx over x over S1. The point being that dx over x is somewhere actually in a differential form with integral coefficients, so it appears in the integral structure on the Ram side, whereas the S1 is maybe dual to a generator of the first singular cohomology group of the multiplicative group. And so this isomorphism is somehow essentially given by integrating a differential form against the closed cycle, and so you get 2 pi I. So this gives rise to the famous periods. And so I'd like to draw in the Ramco Module into this picture. And for this, slightly put this up. It's important to note that the following behavior of the Ramco Module. So I have the Ramco Module for my x, and so I can reduce the coefficients to some prime p. But then actually what I get up to maybe some, if I would do this in derived way, it would be true on the nose. It's just the Ramco Module of the special fiber of x. So for this cohomology theory, reducing the coefficients is the same thing as reducing the space mod p. In other words, I should draw in the Ramco Module here at the diagonal, and this shouldn't intersect. Right? So this gadget here is H1 Ram. And the fact that they intersect here is that's a way to draw the comparison isomorphism, which takes place over the complex numbers. So at this point, infinity, infinity somehow. All right? So we were on the search for a periodic cohomology theory in characteristic P, or Grothendieck, maybe then. And so that's what's called crystalline cohomology. So let me recall the problem. So if y over fp, we have no cohomology with ZP coefficients yet. This exposition. But what we now have, we have a cohomology theory with FP coefficients, which we can just take to be the Durand cohomology of Y. So someone in our picture, if we look over the prime 2, then maybe we don't see the neighborhood, we just see the fiber at 2 of something, and that's this Durand cohomology. And Grothendieck observed is that that there are so-called crystalline cohomology groups. And those are, of the ones I've talked about so far, the ones which are the hardest to get some intuition on what they really are. So denoted by H star Chris. And for some reason, I don't put a comma here, but I put it over ZP. So they are as nice as you would think. So they are finitely generated ZP modules with Poincare duality, etc. And so let me just say one thing, which is in some sense a defining property of them, but you actually have to work to see that this is a definition. The defining property is that, well, assume that we didn't have something which just lived over FP, which actually lived over ZP. Then the Ramco Module of this lift would give you a series we're looking for. If there's a smooth lift of Y, then there's a canonical isomorphism between the crystalline cohomology phi over ZP with the Ramco cohomology of Y tilde. And at least locally, you can always find such a smooth lift. But then you need to see that this is actually independent of the choice of the smooth lift, and that's a bit tricky. So. So in one word, some crystalline cohomology is related to deforming from FP to ZP. Yeah. And okay.
I'm sorry, could you just at the very bottom of the very last column?
Right?
Is that the definition of the Cohomology over the Cohomology of X over FP?
Well, if you have X over FP, then you just you do the same thing. I mean, you just take the Ramco complex somehow for the differentials over FP everywhere, etc.
Yeah. And so that's a theorem, not a.
This here?
Yeah.
Well, if I would put an R gamma here, it would be a theorem, and then put a derived L. I mean, if there's P torsion in here, there's not. Okay. There's a tau one term. Right, so I wanted to draw this picture. So above any prime, now we have a cohomology theory which somehow lives over the fiber and somehow fills in something here. And maybe also at 2, but it's a bit tricky because I drew the arrow at the wrong place. So this here is HI Chris. All right. I have some time left. Right. And Grothendieck tells you that some of the rest of this diagram should be filled in with motifs, whatever they are. But I don't know. I don't understand motifs. So can we fill in more of this diagram by some explicit cohomology theories? And I mean, one thing that's a bit mysterious here, for example, is somehow as you approach somehow going from état cohomology all the way to a prime, and some ital cohomology doesn't exist anymore, but suddenly the special fiber crystalline cohomology exists, and someone maybe would like to understand what happens somewhat to this p-adic cohomology theory as you degenerate into characteristic P. So what happens as ital cohomology in some sense degenerates into crystalline cohomology? And note that the two are two completely different kinds of cohomology series. One is really like singular cohomology, and one is like differential forms. And over the complex numbers, we have this way of relating differential forms and singular and cycles by integrating them, but integrating doesn't work in the p-adic world. So for this question, let's somehow zoom in near your favorite prime, and somehow it's a point P comma P. So what we have there is that we have here somewhere the HI Chris. So we have P here, and we have P here. And then we have the Ramco Module here. And you might complain that because I actually have some canonical lift given, this X of my variety characteristic P, these should actually be the same, but I actually like to regard them as being slightly different objects. But in any case, crystalline cohomology and the Ramco Module are their relationship is pretty clear. But then you somehow have this ital cohomology which lives here generically. So somewhere here in the base, you somewhere have the spectrum of ZP, which is this formal completion of spec Z at P. And then you somewhere have spec QP, which is somehow this formal neighborhood minus the closed point. So that's some kind of punctured disk at P. And over this punctured disk, you can make sense of ital cohomology. And then some of this other stuff. All right, and so the theorem I wanted to state is a recent theorem with Bargev-Butt, in joint work with Bargev-Butt and Matthew-Morrow, which says that one can fill in this diagram by some new cohomology theory. Let me just say 2 words about it. With values in some kind of 2-dimensional complete local ring. More precisely, for the experts, it's Fontaine's ring from p-adic Hodge theory called A-inf. Yeah, sorry. Better? Yeah. So it has values in some kind of 2-dimensional complete local ring. And I guess it's to be expected that it's 2-dimensional because we have like these 2 directions in this picture. And so our theory would somehow fill in all this region here by something which lives over some high-dimensional base. So note that so far all of our cohomology series just had coefficients in ZP or something like 1-dimensional. And so this cohomology theory would somehow at each prime fill in something here. And okay, a few minutes left. So, and this construction is quite complicated, and I don't really understand this cohomology theory, or why it should be there, or why it should behave as it does. Or I will explain roughly how it's defined in a second. Just let me state one stupid consequence of our results is that some of this comparison theorem of the complex numbers tells us that the Ramco Module and singular cohomology have the same rank. But they don't tell you anything about the torsion. In particular, some of torsion classes in singular cohomology don't actually give you obstructions to integrating differential forms. But what follows from our result is that they give you obstructions. Like if you have a p torsion class in singular cohomology, then there is an obstruction to integrating a differential form in characteristic p, which is kind of surprising because it's not at all clear that the topology of this manifold over the complex numbers should have anything to do with integrating differential forms in characteristic p. All right. So let me end with some kind of conjecture, which will also, so in the process of formulating the conjecture, I will tell you a bit about how this cohomology theory actually looks like. Conjecture is that there exists some kind of Q deformation of the Ramco cohomology. More precisely, this cohomology theory will have coefficients in z power series q minus 1, meaning you take the polynomial algebra and an additional variable q and compute it at the ideal q minus 1. Q minus 1 valued cohomology theory. Hi, I denoted by q the wrong of x. So it's a Q deformation in the sense that if I specialize this guy at the point where this Q parameter is equal to 1, I get just the Ramco module of x, at least in the derived sense. Meaning, again, there might be Q minus 1 torsion, and then I have to slightly correct the statement. And this should interpolate this cohomology theory constructed by Bud Morrow and myself among all p. So meaning that if you take this cohomology theory and tensor with and periodically completed, so go to zp power series q minus 1, then you recover these gadgets which we defined for any p. And so if this cohomology theory was there, then I could actually fill in even slightly more of this diagram by somehow going to a formal neighborhood of this diagonal here. And then maybe you might start to wonder what happens near here. And so, no. Right?
Comparing this for different p's, is q still specializing?
No. So I should say that if I take this q Ramco cohomology and tensor from z power series q minus 1 to z p power series q minus 1, that's essentially the cohomology theory. And so why do I call it the Q deformation of the Ramco cohomology? So let me just say how to compute the Q de Ramco cohomology of the affine line. So usual de Ramco cohomology would be computed by the complex times dx, which sends x to the n to n times x to the n minus 1 dx. But now I do a q deformation of this. So I join an additional variable q, which I somehow assume it's infinitesimally close to 1. And then the q derivative somehow replaces is the same thing where I put a q analog of n here. Or better, so let's call this in a dq. Yes, like an easy formula for what this is. So if you take the q derivative of function f and evaluate at x, then you take this q difference quotient, f of qx minus f of x, over qx minus x. But you don't take the limit as q goes to 1. Maybe times dx. So that's the q derivative. I think this has a name. That's the Jackson q derivative. Yeah? This object has been studied. And so you might think, well, okay, I mean, now that you have this formula, you just write it down for a general, smooth, affine algebra, and you easily define this. But the problem is that the q derivative depends totally on coordinates. So the situation is a bit similar to what happens in crystalline cohomology, where again, if you choose coordinates, you can easily write down a smooth lift and hence the crystalline cohomology, but then there's this non-trivial statement that this is actually independent of the coordinates. And there should be a similar result here, and I have some ideas on how one might prove this, but it's horribly complicated to say the least. And I think there must be something simple going on here, but I have no idea what it is. So in the case of crystalline cohomology, it was somehow related to deforming x from fp to zp, and now this is related to deforming x from z to where? It already lives over some of the universal base in algebraic geometry, so I don't know where to deform. Okay, let me stop here.